Hello, today we are going to continue to work on our smoke simulation so that you will be able to create effects like this. So let's jump into Houdini. So this is where we left off last time, and we did the basic setup to create everything around this custom simulation. So today we are going to continue and create the actual simulation. So what we did last time was set up this smoke object that is an empty object, and then we brought in our density volume and called this density, and that created this density object. And we also created a visualizer so that we can see this density inside of the simulation. So next, for a simulation we want some kind of movement, and to have movement we need velocities. So let's begin by creating an empty velocity field. So press tab and type scalar field. And because this is empty, we are not using this SOP version, because the SOP version will bring in an existing field from a SOP network. Okay, so let's connect this scalar field after the density on the left side. And let's call this vel, which is what we usually call velocity fields. And then we want to be able to visualize this. So let's first look at the geometry spreadsheet and open the animation timeline and rewind so we get the latest information. You can see here we have something called scalar field. So we need to rename this. So select it and press P, and down here under data name type $OS, and this will use the name of the node as the data name. And you can see now we have a new object here called vel, that is our velocity field. And because it's a velocity field, of course it's not a scalar field. So let's delete this and instead press tab and type vel and field. Oh, sorry. So this is a vector field. So type vector field. And let's do the same. Connect this on the left and let's call this vel. And select it and press P and go down and use the data name $OS. And now select this and rewind. And now we can see our velocity field. And this is now a vector field and not a scalar field. And to display this, let's create a vector field visualization. So press tab and type vector. And then select vector field visualization. And connect this on this big input on the right side and call this vel viz, like we called density viz up here for visualization. And now if we rewind again, you can see that we have a visualization under the velocity. And again, what we connect here will appear inside of the object we connect it to, just as the density visualizer is appearing inside the density object. Okay, so now we have a velocity, and let's go to the scene view and select the visualizer and press P and enable show guide geometry. And here we want to, because it's 0 right now, we won't see anything if you use streamers. So instead, let's use a plane. And now we see our velocity field. And it does not yet look as we expect it to look. So we have to do some more things with this vector field. So let's press P and go up, and let's look here. We have the division size, and again we have to bring this from the parameters we have. If we go up and look at the smoke sim, we defined this new tab with division size and center. So we can bring this information inside the simulation. So let's go back inside the simulation. And that was the cache. So go to the simulation. Okay. So let's go back to the velocity and press P. And here for division size, type CH and open parentheses and quotation mark. And we will bring this in from the node above. So dot dot and quotation and comma 0. Oh, sorry. A dot dot slash and div size, which is the name of this parameter. And then end parentheses. And now if you click this, you can see it brings in the division size. And we have to do the same with the size and center. So go here and type CH, and in the same way, this is size X, and copy this and paste it into the Y, and rename this to size Y, and paste it into Z and rename it to size Z. And if you click on this, you can see it brought in the size. And now this has the, the correct size. But we also need to add the center as well. So let's type CH and again dot dot slash TX. That is the name that we used for the center. And copy this to the next parameter, that is ty, and the last one, that is tz. And now if you click, you can see we have the center, and this slice is correctly positioned with the correct voxel size. And otherwise we can leave the other parameters as is for now. Okay, so now we have an empty vector field. And let's also change the color here. So let's select it, press P, and let's look at the visualization type. We can change this to speed, so it will show the speed of this velocity field. And this is infrared, so it goes from purple to red. Okay, that's good. So now we have an empty velocity field and a density. And no velocity will still not move this anywhere, but this is the basic data we need for our simulation. So now we need to create the actual solver object. So let's press tab and type multiple solver and connect all the data into the left input and rename the solver to smoke solver. And press P, and let's see, let's go to this geometry spreadsheet. And we don't need these relationships, so let's untick make objects mutual effectors, just to make sure we don't have anything we don't need. And let's select this, and go to rewind, and now you can see inside here we have a solver that still doesn't have anything to do. So now we need to add the actual steps that the solver will execute. So I'm just cleaning up this so we have a little bit more space to work with. Okay, so all the steps for the solver will be input on this broad connector here. So the first thing we need in a solver is to advect the vector field by itself, so that if we have a velocity, then the velocities will also be moved. So let's press tab and type Advect Gas Advect CL and connect this to the first input, and let's call this Advect Vel for velocity. And then press P, and here I would select the most simple setup for now, and you can make it more complex when or if you need. So here I will select single stage, and the velocity field is vel, and it will advect the velocity. So let's add vel under field, and we will use this single step for now. And if you look here, we have a data name that is a bit confusing, so let's untick unique data name, and that will make this very clean to look at here in the spreadsheet. And we now have advect velocities, and we also need to advect our density. So let's create a new Gas Advect CL. So press tab and type Gas Advect CL and connect this on the smoke solver and call this Advect Vel, or sorry, density. So this will take the velocity and move the density along the velocity field. And let's press P to edit and use a single stage, and the field is density. And let's uncheck the unique data name. So now we have here in the data view advect density and advect velocity. Okay, so this is the most basic setup. So now we want to do something in between here to change the velocity, because it's still just 0. But we can run this and see that this setup itself is actually working. Okay, so to change the velocity we are going to use OpenCL, because that's a lot faster than Vex or anything else. So let's press tab and type OpenCL, Gas OpenCL. And this is similar to the OpenCL node that we used in the SOP context in a few lessons back. So if you haven't watched that, I recommend you watch that first. And now let's connect this in between. So I'm going to cut this one and connect this, and then connect this back. And in case you don't know how to cut, you press the Y key and then you get this knife that you can use to cut. Okay, and let's call this turbulence. So we want to introduce a turbulence that will change the velocity. Okay, and next let's press P and For the kernel name, let's type $OS. That will expand to turbulence. And then use code snippet. And here we will enter our code for this OpenCL turbulence. And let's look at this spreadsheet again. And we want a clean looking name. So let's uncheck unique data name. So now we have our turbulence here as well. And let's go to options. So here we want to run over all fields. And we want all the fields to be aligned. And this is especially important for the velocity, because the velocity is actually 3 different fields. So the X component, the Y component, and the Z component are 3 separate fields. And we also want to know the voxel size. So let's tick this. And we want to know the time, so the turbulence can change over time. So let's check that as well. And we want to use a noise data to generate the turbulence. So let's check this. And then we can go to the bindings tab. And here we have to enter all the parameters that we need. So first of all, we have the velocity field. So let's type vel and expand options. And under parameter type, change this to vector field. And this is the vel vector field. And we need to be able to write to this field. Okay, and we also want a few other parameters. So let's press the plus key. And next we want the amplitude of this turbulence. So type amplitude and go to options and change this to a float and default this to 1. And we want to have a frequency, so let's add another parameter. And I will hide the others. Okay, so call this frequency. And parameter type float. And this will be default to 1 for now. And next we will have the number of octaves, because this is going to be a fractal turbulence. So let's press plus and call this octaves. And expand the options, and this is an integer and default is to 1. And then we want to have the lacunarity, and that is the distance in frequency between 2 octaves. So let's press plus and call this lacunarity. And expand the options and change this to a float. And this is normally 2.0. And finally, we will add one more parameter, and this is then the persistence, and that is the change in amplitude between octaves. So call this persistence. And this is also a float parameter. So do the same here, and normally the persistence would be 0.5 in a fractal function. So now we have all the parameters for our function. So let's create the code itself. So go to the kernel and press generate kernel, and this will generate a template that we can expand. So let's select all this code. and copy this, okay, and paste this into kernel code. And we are not going to use the lerp, so you can delete these lines. But instead we are going to use the noise. So we have to include, so hash mark include, and these sharp brackets and xnoise.h. And let's clean up these parameters because we have so little space to write, so we want this to be more compact. So I will change the stride to be called str and stride offset stro, and voxel size, let's call it size x, size y, or v size x, v size y, v size z, and let's put these on the same line to make it more compact. You could also use an external text editor if you want more space to write your code. Okay, so the xnoise, that's quite ugly, so let's just call it xnoise. And val1 we will just call vx, and val2 we call vy, and val3 we will call vz. And this, okay, I will just clean this up a little bit. Okay, so now we are ready to write the turbulence in OpenCL. So first of all, as you saw in the OpenCL lesson, we have to find the index in the arrays where we can find the data. So we have to use something called getGlobalID. And first we are going to use getGlobalID with a 0 as a parameter. And we will make an integer and call this xi for integer or index, or rather integer. And next we copy this and do this again for y and z. And these are 0, 1, and 2. And then we have to use a special formula to calculate the index in the data array. So let's type int I for index equals, so the stride offset, you can just copy this from here, plus xi times stride x plus yi times stride y plus zi times stride z and always end the line with a semicolon. Okay, so now we have the index needed to access our data array. So let's grab our data now. So the data is stored in this Vx, Vy, and Vz. So let's say that, so let's see, float 3. Or just do a float px equal, and here we can take the Vx with the index and cast this to a float. Oh, this is a float, okay. And copy this and create the Y and the Z. And bring this from VY and VZ. And we also have our time, and let's now combine the position and time into a 4-dimensional point. So we call this float 4, and P for position equals, and then a float 4 again in parentheses, and again parentheses with px, py, pz and time. And now we are ready to grab our noise using this position. So let's create a loop so we can make a fractal noise, as you learned in the fractal lesson. So let's type for int O for octave equals 0, and O is less than octaves, and O++. So this will run once for each octave, and then curly braces for the loop body or loop block. And now we can take our velocity. Sorry, this is the velocity. So the velocity x, velocity y, velocity z. So we have to calculate the position as well. And for this we are going to use the x, y, zy that are integers. So let's create the float px equal xi and cast this to a float, and we will multiply this by the voxel size. So let's copy this voxel size and multiply it by the integer voxel number or voxel position in x, and do this for y and z as well. So py and pz, v size y, v size z, and yi, zy. So now we have a position and we have the time, and this 4-dimensional position will work. And for the velocity, we will just combine these into a vector. So let's create a float 3 equals, and in the same way, a float 3 and parentheses and velocity x, velocity y, velocity z. Okay, so float 3v equals. So now we have our position and our velocity, and we can now implement the fractal noise. So what we want to do is to apply a turbulence, and that means that we are going to modify the velocity by the noise. So we will take the velocity plus equal the amplitude times our noise, that is a curl x noise 4, as it takes 4 parameters, the position and time. And we need to use the special x noise first, and then our position, and end with semicolon. And the position should be multiplied by the frequency. So frequency times position. frequency times, and don't forget to save in case it crashes. And next we need to update the amplitude and frequency for the next octave. So the frequency, let's take the amplitude first. Amplitude times equal the persistence. And the frequency times equal the lacunarity. And this is exactly the same thing we did in our terrain lesson, the fractal terrain lesson. Okay, so this will now go for each octave. It will modify the velocity using that octave. And finally, we need to write back this velocity into the velocity field. So for this, we use again the Vx, that is the field for the x position, with the index I, and that equals the velocity, the v, with the index 0. So that is the x component of the v vector. And then the same for y and z. So vy, vz, and v0, 1, 2. And now if we are lucky, this should work. So let's try this. And go to scene view and rewind, and let's play this. And we get an error. So let's see what is wrong with this. Redefinition of Vx with a different type float Vs. Vx equal, let's go into the code again. So you can see why OpenCL is a lot less artist friendly compared to Vex. But it is really fast, so you don't really have much choice if you are going to work with simulations. So let's see again the error code. Okay, so here we use Vx for our velocity field. So let's call this instead val x, val y, and val z, and change here to val. So the val is the field and the v is the current velocity. And then we have to use the same name down here. So val, 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 and save, and try this. Okay, so let's rewind and let's run this. So you can see it's really quick. And let's go to, say, frame 4. And if you look at this turbulence, it's quite big, so we want to tweak the parameters. Let's go to turbulence and press P. And let's go to our bindings tab. And now we have, let's see, the frequency perhaps. Let's set this to double and see what happens. And that is maybe too big still, so let's say 4. And you can see also it's doing too much, so let's decrease the amplitude. So let's open the that's the amplitude, so set that back to 1 and open the frequency and set this to 2 and try perhaps 4. And for the amplitude, maybe half, let's see. And we also want to make this a fractal function, so let's add the octaves. So open the octaves options and set this to 2 and increase one more to 3. So now we have a quite interesting turbulence field. And you can also go to your visualizer and change this to use streamers. And that will be a little bit slower, and it will actually make these streams so you can see it in a more interesting way. And because this is slowing things down, I'm going to disable the velocity visualizer. And let's rewind and let's play back our simulation. Okay, so this looks quite interesting, and you can see how fast this is. It is almost real time. And because this is so fast, you can actually, let's go back up to the parameters and press P. And here you can decrease the division size so we get a higher resolution. So I'm going to set this to 0.005. So now we have a really high resolution, or quite high resolution simulation. And go back in and rewind and play this. So it's going to take 4 times as long, but this is also 4 times more data to process. And still it's very fast to simulate. So you can try this and tweak your parameters inside this bindings tab in the turbulence. Actually, this is still not really a smoke simulation because this does not behave like a real smoke yet. So we have to do one more thing. So let's go back up and let's go down again to 0.01 in division size. So we get a quicker simulation. And let's go back into the smoke sim. And this is really the most important part of any kind of smoke or fluid simulation. And that is the Project Non-Divergence. And that makes sure that if you go somewhere here and look again at the velocity field. So this will make sure that these velocities are non-divergent, which means that they will behave like a fluid. So to do this, we need to add a Project Non-Divergence node. So let's press Tab and type Gas Project Non-Divergent Multigrid. And let's rewind so we don't run all the steps. And connect this after the turbulence. So I'm going to cut the advect density and connect that last here. Or you could also select the solver and move them using this interface like this. Okay, and this is quite an ugly name, so let's just call this P and D for Project Non-Divergent. And let's press P and go to the geometry spreadsheet as well so we see what we are getting. So this is quite ugly name, so let's unclick unique data name and rewind. Okay, so now we have P and D. And we don't have any divergence field, so let's delete this. And we don't have a pressure field. And you only need these fields if you want to use them for something later. And let's click use OpenCL so it's faster. And that should be good enough for now. So let's press P to close the properties. And now we have our full simulation with the data to simulate the velocity advection, the turbulence, the project non-divergence, and finally the density advection. So let's look at this. So rewind and play. And now this is behaving a lot more like a smoke, as you can see. And it's really, really fast. And again, you can tweak your frequency and amplitude and the other parameters to make the exact look that you want. Okay, so that is the custom smoke solver fully implemented in OpenCL. So let's go up, and then you have your top import to bring in your simulation, and then your cache. And here, I called this EXR last time, so let's change this to geo instead. So in my case, the data geo heap name $OSF4BGOSC, and then press save to disk. And now this will cache this. And that's done already. And then we have our smoke that we can render, and we have our render set up. If you go up, you have the ROP-net, and here you can again do all these steps. So run the simulation, batch the full simulation, and then run your render. And it's good enough to render this using OpenCL. And then once you have rendered this result, then you can take this into, for example, Nuke and apply your effects. So let's just clear the playback cache. Okay, in this example I have also added a buoyancy, and buoyancy requires a temperature field. So you can just continue and expand and add like temperature or burn fields or flame fields and create as complex a simulation as you like. So I hope this was helpful, and see you next time. Over and out.